Okay.
How many hours are in a month?
Huh?
I said, how many hours are in a month?
I don't know. Do the math.
How many days are there? 30.
Are you sure? Are you counting February?
It's
On
It averages out to 30, so
it gives you.
How you know this number?
I'm working on it right now.
We are almost done, Doctor.
Somewhere that the number is actually like stated.
Oh.
Somewhere like in the data or somewhere. I remember like it's
I didn't think you needed it.
the number of hours a month. You definitely need the number of hours a month.
Yeah.
Well, I mean, you end up,
Question
Oh.
5, part A
You need the
is,
number of hours a month.
when you do the statistics, you tally a total, so that's where I got it.
And then one of the questions says, now multiply the value
Yeah.
you got by the number of hours in a month.
oh yeah, right there.
So are we just turning in, if we do problem 5 and problem 6 on Excel, do you want just the Excel files?
I am going to address that very question during class today.
Fantastic.
Sweet.
I was about to ask the same thing.
I just put
Already
the,
turned mine in, but
In fact, I'm gonna stand on a little soapbox about it and make a big speech.
I was gonna say that in the last class because you were talking about the height of the whiteboard. You should actually bring a soapbox. Stand on it.
I totally should, but where do you get a soapbox these days?
milk crate.
Yeah, you can do that
I-
challenge.
The milk crate challenge!
While you're at it.
I need to focus on getting.
Oh, sorry.
Yeah.
It's too easy to get.
Okay.
Where's my calculator? The soapbox.
They know it.
Do that, man.
I think it's a 31-day month.
It's 30.4.
yeah, I used it.
Are you sure even when February has 27 days?
I googled the average days in a month.
You could just also do
It's 30.
365 divided by 12.
I think I did I seem to remember I did 744.
Yeah,
Or 740 or something like that. I mean,
yeah, 744 hours,
okay.
which is 31 days.
Online now or not really?
No, I didn't watch it last. Should have watched it last. So we did. Pages.
I think that's fun.
Go to the other incident.
There was only like a few extra pages from doing.
Oh no, I remember Friday. I had like 4 pages.
You can take that number divided by the total. So that gives you,
Okay.
by the total number, well, by the total number of.
Yeah.
So it would be a PDF instead of histogram.
3 pages.
This is when. I must be tripping. There's like only like a quarter of the class here right now.
Well, it's not even 10 minutes, or it's, I guess 9 minutes till we start, so.
Ah, okay, there it is.
Oh, I'm an idiot. The data just contains the 1 month.
Yeah,
Yeah.
that's That's why, like, the number of hours in there is. I think
Grab your own bite.
I think it's a 10-minute.
Yeah.
It's 10-minute intervals, yeah.
It's 4 PM, bro, it's okay.
It's all right. I think everybody has had a, oh my God, I'm an idiot moment, and if you don't have at least 2 a day, it's probably not a whole day.
I think I had at least 2 of them today, because I had one earlier while we were doing
Yeah, if it
question
makes
four.
you feel better, I wouldn't have even suggested that.
He literally says it in the homework.
This is the day to take it for 1 month and 10 minutes. Every 10 minutes.
Yeah, I was kids like that. Super boring.
I'm hoping it's on the.
Choose the C and K. If it's a C and K, not the numerical values, the C and K. I'm like, why isn't my equation working? Like, why is it giving me like an error?
You can just pull a chair and make it work faster. You can just pull a chair.
I don't know, it sounds like a people thing.
It sounds really. The problem that.
Yeah,
Design
totally, like,
problem.
it's more.
It's wow. That's over here. This is like a 25 and a half meeting.
Well, one of the projects is
It's almost like
Half this thing is data point. Those are 10 minutes each. So go. It's 744 hours.
material side and do it.
But you should be able to tally that with your data.
maybe that's not your assigned. Like, can't play something.
Okay, look, I'm always steal your calculator.
I'm not even sure. Oh, it's in here.
That's number 4.
Yeah, we were doing it
All
just
homework for this.
backwards.
12 because, yeah.
He was doing the actual one, I was doing the other direction. Okay.
Define something new.
Yeah.
Literally, you wanna do this.
I wanna do it.
Yeah, sorry, I don't have the clothes for it. Alright.
Yeah, no.
Is, Okay.
Function. I don't know.
Okay, but you are a student who's heavily involved at the very least, and you're one of the, you're at least believe as far as.
I can do it.
And you can get basically.
Or in a metal shop.
I was gonna have to ask you your last or the other.
I know they have a good one.
Caleb, did you grab your?
What's that?
Maybe.
Wait, one more thing I get to set up for class.
Butter, jelly, yogurt, and some cheese.
And then, yeah, I got 5 minutes all.
Well, that's better. I just mixed it. Why would you?
No, for
Yeah.
understanding.
You know what? Yeah. I would like to read.
I don't like to like.
Who's up? Carly or is it?
No, I was Ducati. Ducati, yes.
It was so funny because my background was playing sound. I had no idea that you're like, in class. So like after class, I was stuff on it. So I was-
Scrambler, that's what it was.
That's my background.
The great scrambler.
Like if you couldn't take a pass at your thing.
I know, well, so that's the thing is that I to get a, so he's like, okay, so we're gonna.
Is there one or something?
No, I don't have the license.
No,
It's like,
one.
it is. Like,
It's true. A lot of people get bikes before they get their endorsement.
No, I'm on problem.
True, I'm like,
Which one's
okay,
fine?
I guess
It's
this
the
is
one
true.
with
I
the
could get
data
a
table.
bike and then I'll have to
A little
learn
bit.
how to ride so that I can get the license.
I'm not sure.
I'm there, bro.
You have the Excel?
Oh, it's not gonna be good.
Instagram. Oh. I don't know if that's all that. I don't know.
No,
I didn't get that far.
no, I used for the Bible one. Oh, you're doing a complicated of math?
Mhm.
Oh, I just did that. He said it in a simple way. He's like, what the height of them? Or whatever. So I was like, so this is the original one, and I just saw it. So we didn't have to Where is it?
No.
Literally. I didn't do it by a function. What? It's like she's in the wall. Number 2. You're always gonna think this time you're
We moved. I'm gonna check corridors down.
Oh, hey, you wanna do that? I got to quick. Okay. All right, I figure we have 2 minutes to talk about Dan.
Yeah, I gotta do that. I gotta not to. Get some. Siesta. I'm not use all the that's what I have in Look at this now.
I'm sure I used all the data points. You got the drive. Running the drive event. Yeah.
Oh, one more. Okay. I have 4:15. Let's go ahead and get started. If you can see, I hope you can see the document camera. I want to go over quite a bit today. Bremerton, can you hear me all right? And are you seeing content?
Yeah.
All right, and Coleman, can you see me? I can see myself. And you,
Yes.
you're seeing content as well, and I guess you can hear me. Okay. So we here in Everett, we're in a new room today. This is probably going to be our room from here on out, just because they've had less issues with this room. I think that might be because less classes are taught in this room, but I don't know. So so we're in a new room today, and I'm feeling a little bit more comfortable with going back and forth between the computer and the document camera than I was in the last room, because that seems to always mess anything up. So I want to spend a little time. We've been in chapter 3, but I want to go back to the last little bit of chapter 2, and I want to show you guys and talk to you guys about some wind data, like collecting wind data and what wind data is out there and available, and what are the devices we use to collect wind data, which I did cover, but I covered it really, really quickly. I didn't get to show you the websites I wanted to show you. And then I have a homework question for you guys about homework number 1 that the TA brought to my attention. And since I'm asking you about a homework question, I feel like I should open it up. You guys, you have homework due this at midnight, right? Midnight. Okay. So if you guys, I fielded a lot of questions about problem number 5 and number 6, which are related. And I thought maybe I'd try to clarify those questions. And then I wanted to bring up something. I want to get on my little soapbox about something I'm going to call professional skills. That kind of relates to a conversation I've been having with the TA about an email that one of the students sent, and nobody's in trouble or anything. I just want to give you guys my 2 cents worth of it. I want to give you some advice that you can take or not take. And I figure most of you won't take it or won't really digest it, but hopefully you'll digest it at some point early in your careers. You know, remember, oh yeah, Dr. Kalb said that. And I want to talk to you about something called the collegiate win competition, which I've been kind of keeping my mouth shut about because I thought until yesterday, I thought only students that ever could participate in that, but I want to talk to you guys about that. And then the big topic today is we're going to kind of go aerodynamics 101. The last 2 lectures have been pretty math intensive. We got pretty deep into some mathematical theory and some physics derivations. We're going to do that again, but not today. We're going to first kind of take a step back and kind of look, okay, now that we've done 1D momentum theory and gotten all we can get out of 1D momentum theory, we're going to take a look back and think, okay, let's get the big picture on airfoils and aerodynamics. Okay, so that's the plan for today. So I'm going to start, if you guys don't mind, I'm going to start kind of like just quickly go over what I wanted to discuss about chapter 2, and then we'll talk a little bit about homework and so forth. So I'm still going to go through this fairly quickly, but this is take a way back machine to like, I don't know, like 2 weeks ago. And I have already posted these notes. Just the last couple of sections in chapter 2, when I was talking about, we spent the whole chapter, and now you guys are working on a homework about wind data that's out there, how much energy is in the wind, how to predict how much energy you can get on the wind, if the wind is blowing at average wind speeds. I want to talk a little bit about how this data is collected and what data is generally available. So if you're going to build a wind farm, you need data. And you need data not just because you need data to know how effective your wind farm is going to be, but you need data because you're going to need a loan. You need to borrow money. And no one's going to loan you money unless they have that data. Okay? So what type of data are you going to need to collect? You need to know the wind speed. You need to know the average wind speed. And as problems number 5 and 6 demonstrate, you probably need like some very large time series. The data set we're working with on the homework is over a month. You probably need over a year. And once you have that time series, you want to know the average wind speed and you want to know the standard deviation. You also want to know something about wind direction. You also want to know about how much turbulence is in the wind. And you want to have some sense of if there's big variations in the time of in the wind speed at particular times of year, particular times of day, and so forth. And so there's lots of devices that we have for collecting wind data. The most common and the one that the banks like the most is the cup anemometer. The anemometer is just a big fancy word for a device that measures wind speed. And they also usually measure direction as well. And it's a pretty straightforward device. It's just a device that's made of these cups. And when air blows against them, the drag on one side of the cup is different than the other side. And so they'll rotate at a certain speed, and you have some type of probably Hall sensor or some type of sensor that measures the rotational speed of these 3 cups. And you can relate that to wind speed. And then you usually have a vane connected to some type of sensor that gives you direction. And I don't know Pullman campus and the Bremerton campus, if their students all take the same classes at the same time like our students do, but most of the students here are currently taking ME 306. And ME 306, you learn that look, whenever you're measuring anything, you don't weigh whatever the scale says you weigh. The wind speed's not blowing at whatever the device says it is. You have to look at the accuracy and the precision and the repeatability and the response time, et cetera, of all this. And so you need to consider that whenever you're selecting a device. In the United States, typically, banks are gonna want you to have, put up what's called a met mast, which is short for meteorological mast, and put that up, and have that up for a year, where on a met mast, you have at various hub heights, and they call them hub heights, because it is where at the various heights one might be interested in putting the hub of their wind turbine. And you'll have anemometers and also devices that might measure like air density and air temperature, and barometric pressure, as well at various heights above. So what you'll end up with is a time series, not just one time series data, but a time series data at like 10 meters, at 30 meters, at 60 meters, 80 meters, 100 meters, and so forth. In the United States, we have had a multiple over the years surveys of how much wind energy is available at all locations inside the United States. And probably the same with Europe as well. So there's a lot of data that is out there. That data is collected by an organization called the National Renewable Energy Laboratory, or NREL for short. Okay? The way this data is collected is they've taken met masts that are known, where whoever put up the met mast is willing to share the data. Any type of existing monitoring stations, such as airports. They do computer modeling and extrapolate wind data between met masts, or where met masts are not available. And they use satellite data when that's available. These atlases give you a general idea of the wind energy potential on given sites, but they're not the end of your journey, they're the beginning of your journey, okay? You're probably gonna have to put up a met mast wherever you're planning to put data. And I don't want to spend too much time on this figure, because we discussed it before. In the US, potential sites are given a wind power class, and this is a table from your book that describes what wind speeds and power densities are necessary to be referred to as a power class 1, power class 2, and so forth. There's a couple of websites I'd like to show you, and I've got them, these websites I've linked to in Canvas, and I'd like to show you these websites, and I'd like to use showing you these websites as a way to slide into talking about the collegiate wind competition. Before I do that, I also want to introduce you to the concept of a windrose. So when you're designing a wind farm, you need to know, am I going to put a wind turbine in the wake of another wind turbine? The thing is winds change direction. So you can't put a wind turbine anywhere without it somehow being in the wake of another wind turbine at some point, okay? So what you actually need to know is just like we look, what is the probability of the wind speed being a particular speed over the course of the month, we also need to know what is the probability that the wind is going to be coming from one direction or another at a particular time of the month. So a windrose gives you this information. So you can see here that the height of each of these somehow represents the probability or the likelihood of the wind blowing in that direction. You have to be really careful though with windroses, because as you can see from these two examples, and again, this is a figure from the book, the definitions of what the colors mean and the heights mean can change from windrose to windrose, okay? So be aware of that. When you get into actually designing a wind farm, you take all of this information from a met mast, and you use some type of application, of which there are several. I'm familiar with open wind. I intend to teach you guys open wind at the end of the semester, although I might change my mind. There's another program called Wind Farmer. There's another program called Continuum. I just learned of another one today that's from a Spanish company. And what these applications can do is they can look at, if you put a wind turbine here, and put a wind turbine here, wind turbine here, what percent of the time is each wind turbine going to be in the wake of another? How is the level of turbulence? Because each wind turbine is not only going to reduce the wind velocity, it's going to increase the turbulence of the wind, and can make a prediction about how much power you can get or energy you can get over the course of a year from a particular wind turbine. Open wind can actually do an optimization routine to attempt to find the best location. And this is all, most of these are examples of GIS software. So what I'd like to do now is show you those two websites. And one of the nice, this room seems to not foobar. Let's see if it works. Every time I switch from the document camera to the computer. Okay, Pullman, Bremerton, you guys seeing the computer screen now? Okay, all right. So I put up, I created a new module just called class resources, and I have a link here to United States wind data. And if I click on that, it links to two websites, which I've already pulled up, so I'm just going to pull them up. The first one I want to show you is an NREL website, and you guys can look at this website, access it to it. It's called Wind Prospector. And this website is an example of the power of GIS software. It is an example of, this website was created using GIS software and GIS tools. And what you're seeing here is actually a user interface for kind of a web cloud-based GIS software. Remember, GIS stands for Geographical Information System. And this is essentially the way it works, where you can have a map and you can have different layers. And I can turn on and off different layers. So if I want to turn on wind resource, land-based wind speed at 80 meters, so this would be 80 meters, that'd be the hub height of 80 meters. And now I turn on that channel, and I can see a color coding of where the different colors represent the wind speed at these locations. Now, again, this is part of the NREL data set. So that doesn't necessarily mean that somebody's actually put up a met mass and someone's actually measured the data, the wind at every single, I think each pixel on here represents 1 square kilometer, okay? They haven't done that, right? They've used mathematical modeling and CFD, computational fluid dynamics, to model what the wind will be doing based on the nearest possible net mass. With GIS software, you can design, so each one of these things I can click on and off could be referred to as a layer. And you can turn on and off, and you can create layers that have things like wind speed, terrain height, terrain roughness. Because remember, roughness affects things like how thick the atmospheric boundary layer is. You can have a layer that has road information, where there are buildings, where there's water, where there is very large changes in elevation, which might make it difficult to build a wind turbine because it's hard to build a wind turbine on a steep hill. And with GIS software, you can, this is a user interface, but with GIS software, you can add all this information to a GIS database. Again, people get, my sister-in-law, my brother's wife, she went to school for 4 years to get a degree in GIS. But you can learn and start getting practice with GIS software, and learn it going through a few tutorial sections, okay? And we'll be introduced later in the course to some GIS software. The other website I wanted to show you, and I link you this website, it's kind of being a jerk. I link you to this website, but you can't use this website, okay? Because you need it. This website is owned by a company called UL. Well, okay, so UL is this huge multinational corporation that's mainly focused on safety standards, and UL you may see on like any electronics good that you have, there needs to be a UL sticker on it, or an electrician will refuse to help you plug it into a wall. Not that I've had any fairly recent personal experience in it. But UL bought this renewable energy wind company called AWS, and they made Wind Prospector, or they made Wind Navigator. What they've done is they have the same wind speed data set that NREL has, plus they own some private access to wind energy data, and they have supercomputers where if you can't afford to put up your own metmasts, they have computer simulated time series based on statistical analysis and CFD of to get approximate solutions. So, and they can sell you wind data for a particular location. So in order to use their website, you need to have an account with them, which I do because I bought wind data from them, and their wind data is like really expensive. Okay, so for example, last year we were interested in building a wind farm in South Dakota. And you can look at this picture and you can understand why we were interested in collecting data, building a wind farm in western South Dakota, because there's a lot of wind speed there. Okay, so you select a site and you can zoom in, and at this one, you can zoom in, and you zoom in far enough, you can see roads, you can see satellite, and this is based off satellite image. And let's say I wanted to build a wind farm right there. So I can click on this point and click add to cart, and it's going to say, I want a typical year, and it's asking me for hub heights. So I can put in various hub heights and where I'm interested in heights that I might be interested in building a wind turbine at that height. And you can see that they're 1 year of data they want to sell for me for almost $1,000. Okay, so that's how much people pay for them. It's like this information has monetary value just attached to this information. Okay, so I just wanted to show you guys that. All of this is leading into a little conversation I would like to have, mostly with the people in Bremerton and Pullman. So I'm going to close this and I'm going to open up a PowerPoint presentation. All right. So on the Everett campus, we've been involved for the last 3 years in something called the collegiate wind competition, and we're involved in it this year. And the collegiate wind competition is a competition that is sponsored by the United States Department of Energy and also NREL. It's sponsored through NREL, the National Renewable Energy Laboratory. It's a competition to get, at least up to this year, to get into the competition. The faculty at a university have to write a proposal for the students to be involved in the competition in the following year. And when we wrote the proposal as WSU Everett, partnered with Everett Community College, which is a community college located right across the street from where we're at. Because I knew I was going to be teaching this class, I asked NREL if it was okay if students in Pullman and Bremerton who were interested in joining our team could do so. And they needed to think about it for a while. They got back to me yesterday and they've approved. So if anyone in in Pullman or in Bremerton is interested in joining our collegiate wind competition team, you can let me know via email, or you can let Caitlin Jones. I'll show you this. Can you guys, I know you guys can see the content. Can you see this board right behind me? If I write something on the board, can you? Okay. Actually, I don't even know if I.
There's one of the next three.
I brought my own. All right, so you can email me, or you can email Caitlin Jones, who is one of the leaders of the team. It's supposed to be a student-led team, so I am telling you about it. But the way our students, that's right, I don't know how to spell Jones. Actually, I don't know. She spells her name in a weird way. She puts a 1 after her last name. It's weird.
Oh, that's the edge of the board. We can't see past the W.
Okay, it's su.edu.
Sure, yeah, I was gonna say, I'm sure we can assume the rest.
And what she can do for you, if you're interested, is she can give you the Discord link. Because our team, pretty much all the student teams on this campus love Discord. So we are one of, I guess there's 16 schools this year, or there's 13 schools or 12 schools and 4 learn-along schools. And we're in this competition. We've been given money by the federal government to be in this competition. The competition is a year-long competition, but it does culminate in an on-site competition at the end of the year, just after our school year ends in San Antonio. And if you're involved in the team, I mean, obviously there's 80 students in the class, but all 80 of you decide to become an active member of the team. We're not all 80 going to go to San Antonio, but we have enough money for about 15 students to go. And probably 4 of those students are going to be Everett Community College students. There are 4 parts to this competition. There is a building a turbine prototype part of the contest. There is a turbine testing part of the contest. The turbine testing part of the contest will be done at the physical competition. There is a project development portion of the contest, which I am really hoping, because obviously it'd be weird to do, it's hard to do a remote team, but the project development contest is very much a part where students who are not located in Everett can definitely play a part. And then there's another part, which is a connection creation contest, which is really focused more at communication skills. And again, if you guys have any friends who are communication majors who might be interested, we can talk more about that. The project development part this year, I included this slide just to point out, so it's a year-long contest with deadlines throughout the year. But the big payoff is May 16th through May 19th, which is shortly after finals week. And so you all have graduated, relax a little bit, and then go to this competition in San Antonio. This is also, the competition is being held at the Clean Power, the ACPA, which is America's largest wind energy industry group. So the competition is going to be held during their big conference. So you'll be mingling with people from industry. You'll be showing off your work to people in industry. It's a great networking environment. And so I wanted to kind of focus in on the wind farm development. This was our wind farm design from 2 years ago. To me, it looks like a prancing dog. This was in eastern Colorado. And this is something like the students built this using GIS software and using OpenWind. Last year was in South Dakota. We selected 3, we had like 3 sites we down selected from. This year, the big theme of the competition is offshore. So we've actually been given, this came out blurrier than I thought it was. So this is, the rules for the competition were just finally posted yesterday. And so the federal government has created leasing sites for possible wind farm construction. And the rules for this year are that we need to build an offshore wind farm somewhere in site 2. So around this circle with a 2 in the middle of it. And then I've just got a few slides of, so offshore wind farms, wakes. If you're going to talk about the effect of wakes on wind farms, I believe this picture is required by law to be in your presentation. This is a wind farm off the coast of Denmark, and the wind just, there have to be a marine layer that day, so it was really obvious. You could really see the turbulence and the velocity deficit of the wind farms on the wind turbines behind it. And the wind happened to be going in a direction where you can see all the wind turbines that are not in that front row are in the wake. Oh, cool, it's gonna work. So, and this is from a paper, from a research group in Switzerland. And they actually showed what you're looking at here. This is a CFD simulation, computational fluid dynamics simulation. But what you can see is when they have these wind turbines that are evenly spaced like this, what you're looking at the bottom is kind of a simulation of what the wind speed would be doing as the wind changed direction. And on top, what you're looking at is if one is the maximum power that this wind farm could produce, you can see this giant dip where the amount of power the wind turbine can produce at a steady wind speed as the wind direction changes can drop by almost 30% by the wind changing its direction by just a few degrees. So it just gives you like a sense of, okay, what are the types of things you need to be thinking about when you're developing a wind farm from an engineering point of view. And I think that's, and this was like some research I was thinking I possibly could have done looking at the effects that turbulence has on wakes. And that was what I wanted to share with you about the wind competition. So again, if you're interested, you can email me, you can email Caitlin. I'd love to hear from some of you. And if you're interested in other aspects of the competition besides project development, that's fine too. I just think that'd be a good spot for people not on the same, but I think location. But I think if anything COVID-19 taught us, it's that we can do things remotely. Like we can work together even though we're not on the same space. All right, I am for the moment done with the computer, so I'm going to go back to the document. All right, so just to get this out of the way. So the TA sent me an email saying when he graded homework number 1, and said that several students answered the questions that involve how much power is available in the wind using this equation. And he didn't understand where this equation came from. And I looked at it and I don't know either. So I'm kind of curious. And you know, don't feel don't be embarrassed, but I'm curious, you know, obviously you're not going to speak out in class and go, oh yeah, I use that. And I'm guessing it comes from like some like aerospace class. But I'm curious if somebody could email me and let me know what that equation was. It was like 4 over the square root of 3 times air density. There was some, I don't know if it was a constant, but there's a 1.19, and then it was times the wind speed. And obviously the amount of power, in this class, we've learned that the amount of power that's available in the wind is the wind speed goes as wind speed cubed. So I'm not sure where this came from, but we were both curious. All right, and then I wanted to talk about this. So, all right, this has nothing to do with wind energy, but this came from an email, and the person who sent me this email, you're not the only person to ask the question. But I got several people ask me the question in this room right before class started. And the question was, you know, on this homework that's due tonight, the homework that's due tonight, there's several stuff which I said to you can do in Excel. I didn't actually say to use Excel. I said you can use Excel, you can use any software application you want. I asked for some histograms. You can draw them by hand if you want. Okay, I mean, that's legit. I mean, like, you might want to use Excel to process the data, but actually creating a histogram in Excel is somewhat, in my opinion, laborious. And drawing a histogram and then dividing it each column by a constant, I had to kind of like budget in Excel. I mean, I just took the data and retyped it in and created a bar chart. I mean, and which people who come to my office hours, they did the same thing. I mean, so And what I told the student who emailed me is, no, please do not submit it in Excel. Please submit it, just look, copy and paste it, put it in a document, or put it in some way so the TA doesn't have to open up 2 documents for every single student. There's 80 of you. He's only supposed to work 10 hours a week. If I assign homework, I'm not, by the way, but if I was going to assign, I was really trying to assign a homework every week, that would be like, he'd have like 6 minutes to grade each person's assignment. But I never said that to the class. So look, if you did it, and the CA emailed me and goes, by the way, Dr. I don't want it. Okay. So if you want to do that, I mean, he's not going to take points off for it. Okay, and I confirmed that with him. He says he's not going to take points off for it. But I kind of feel like it's my job to teach you not just wind energy engineering or statistics or thermal system design. My job is to teach you guys to be successful engineers and successful in your careers. Okay, and I think it's a really valuable professional skill, and it's not easy, and it's not something that comes natural. But to think about when you take work that you've done, and you're handing it to someone else, whether that be a superior in the company you work for, that be somebody who is at your level, or that be somebody who is, beneath you or has a lower paid job than you in the same company, to think about how are they going to receive this data? How is the work I'm presenting them going to affect them? And I guarantee you, if you make their job easy for them, they probably won't notice. But if you make their job hard on them, they will notice and they'll remember you. Okay? And trust me, in times where I have accidentally slipped and failed to make the life easy on somebody who is, quite frankly, I don't want to think about it this way, but lower paid than me, generally lower in the, and it has come back to, lower in the award chart or whatever, it has come back to haunt me.
Lower in the weight.
Okay, it hasn't happened a lot because I'm really good about it, but the times it had, almost every time, I'm like, oh man, I wish I didn't send that email, or I could have made that clearer, or it has come back to haunt me. All right, so little things like when you submit a file to somebody, did you name it a file that is meaningful to you, or do you make it meaningful to them? Did you think to yourself, I'm sending my resume. Is this person getting 1,000 resumes, and so 1,000 files called resume, or 1,000 files called homework 7? How can I make this clear? The file name, make it clear that this is, this particular individual homework 7. Things like, I don't know, there's a lot of memes on Facebook and on the internet about like, why do you have to submit your resume and fill out the online job history on every website you search for a job. Just do it. All right, just do it. Because there is logic behind it, is because the person who's going to interview you, they would like a one piece of paper that has your whole, that they can glance at and kind of get a sense of who you are. The search engine, or the people who are like deciding who are the 5-6 people going to be interviewed, they're probably using a computer algorithm. Okay? If you have your resume, it's only going to take you like 5 minutes to like copy and paste that. You have an electronic copy of your resume, so you have a Word version or a Google Doc version. Just copy and paste the stuff into the form. All right. But one of the things they're looking for is this the type of person I want to work with? Is a person, if you're the type of person who's like, I'm not going to do this, I'm just going to say, see resume on that form, you're obviously you're not the kind of person who tries to make the other people in that organization's lives easy. Okay? So that's just, all right, so that's just my soapbox. I imagine that just like went over it, like, that's just like old person talking for 10 minutes. Gosh, but at least if 2 of you out of a class of 80 internalize that, I think it was worth our class time. And if not now, then maybe you'll internalize it later in your career.
Okay.
All right. I'm going to step off. It's a big Dr. Top soapbox here. I went on a soapbox in thermal system design, but at least that was a soapbox that was trying to like give you hints for one of your other classes. All right. All right, so with that, I should probably say, any questions about the homework that's due tonight, particularly about question 4, 5, and 6, because I know I've gotten a lot of questions. I will say one of the questions I've been getting a lot is people were confused by the phrase, use the center value of the bin. What I meant by that is the bins are supposed to be like from 0 to 2 meters per second, no, 2 miles per hour, 2 miles per hour to 4 miles per hour. I'm just saying, use the value 1 mile per hour. That's the center of that bin. Assume all the points, all the data samples that are in that bin from 0 meters per second to 2 meters per second. Let's just say they were all at 1 meter per second. Multiply the number of hours that the wind was blowing at 1 meter per second by the power that's produced if the wind was blowing at 1 meter per second. Multiply the number of hours that your histogram says the wind was blowing at 3 miles per hour by the amount of power that would be generated at if the wind was blowing at that speed. That'll tell you the amount of energy that was produced over the course of the month at the time the wind was blowing between 2 and 4 miles per hour. Just keep doing that for all the bins and then add them all up. That'll give you a good estimate of the amount of power that was produced by a wind turbine, that particular wind turbine over the course of a month. Right? That's what I was asking. And then question 6 is like basically do the same thing over again, but rather than use the real world data, use a Weibull distribution or a Rayleigh distribution. Also, another hint I might give you, a Rayleigh distribution is just a type of Weibull distribution. And I remember correctly, any Weibull distribution with a K value of 2 is a Rayleigh distribution. Right? So that might make things easier on you after all you've done it. All right, did that spur any questions, or can I move on to talking about aerodynamics 101? All right, aerodynamics 101. And we're going to be talking about this today, and we're going to be talking about aerodynamics. We'll probably continue this through Friday's class as well. All right. So I'm going to draw in, and I'm going to call this this is the wind. This is not u infinity. This is u relative. This is my relative wind velocity. This is the wind that my airfoil sees. Right now I'm just talking about an airfoil. It could be a wind turbine. It could also be an airplane wing. Airplane wings or airfoils tend to have a shape that looks something like this. I don't know how well you guys can see color. That was supposed to be blue. I'm going to try to use pink. Maybe that'll be a very different color. This point right here is called the leading edge. And this point right here is called the trailing edge. A straight line that goes from the leading edge to the trailing edge, which isn't always necessarily through the actual, it might actually leave part of the airfoil. This line is called the chord line. And the length of the chord line is given the notation C. So C is the length of the chord line. A line that starts at the leading edge and is 1/2 the distance. I shouldn't say a line, it's called a line, it's really a curve. Where this curve is 1/2 the distance from the bottom of the airfoil to the top of the airfoil, is called the camber line. Okay. And I drew this as a airfoil with a lot of camber on purpose, and it's somewhat exaggerated. Sometimes airfoils, and a lot of airfoils that were used, I don't necessarily now, but definitely in the early days of wind energy, they were symmetric. Okay, so this is a symmetric airfoil. Now, the wind speed I purposely drew, the relative wind speed I purposely drew as horizontal. And my chord line is not in line with the wind speed in either case. So this is my chord for this airfoil, and I've already drawn the chord for this airfoil. The angle between the wind direction, the relative wind direction, and the chord line, and I've drawn this somewhat exaggerated, is called the angle of attack. And you either see it as AOA or you see it as alpha. All right, so I'm not going to write down these definitions because I've already said them verbally, and when I post the notes, you'll see the definition. But we have our chord line. We have our chord, which is C. The chord line is the line itself. The chord is the length of the chord line. We have the camber line. The camber, which I haven't said yet, the camber is the distance between the camber line and the chord line. And it's not necessarily constant. So if it's symmetric, like this one, then the camber is 0. Okay, and having a camber of 0 and having a maximum camber of 0 and being a symmetric airfoil is synonymous. And those two, there are 2 ways of saying the same thing. We have angle of attack. Which is AOA, or we can write it as alpha. I tend to write alpha for angle of attack. And I generally think it seems like older textbooks tend to use AOA. But AOA is nice, pretty obvious that's angle of attack. I'm going to introduce you to another term, NACA. NACA stands for National Advisory Committee for Aeronautics. And the reason this is important is because different airfoils are often named after the organization that did the research on the behavior of that airfoil. And NACA in this country has done a lot of this work. So typically, you see airfoils are referred to as like a NACA 0012, for example. Okay, so you'll see things like NACA 0012, where the 00 refers to the camber. So this would indicate a symmetric airfoil. And the 1-2 represents the thickness. And I'm trying to remember off the top of my head, I think what it is that the 1-2 represents the fact that at its thickest point, there is the airfoil is 12% the chord, okay? Now this is a 4-digit NACA. There's also a 5-digit NACA. I think there's also a 6-digit NACA. There is an actual mathematical formula. There's an actual mathematical formula for the shape of an airfoil for a 4-digit NACA airfoil. In fact, I didn't plan on doing this today. Let me probably find this website. Probably find this if I can get my computer turned. Yeah, it's a really nice Wikipedia article. So this is just a Wikipedia article on the NACA airfoil. And there's a 4-digit series, and you can actually see this is the mathematical expression for the height of the top of a 4-digit NACA airfoil, where again, the 00 is the camber, the first 2 digits are the camber, the XX is the thickness, and you can actually find Y as a function of X, and you can actually create, okay, this is the shape of a NACA airfoil. Okay. So what NACA did, and by the way, so NACA, this was all like during World War II, right? Between World War I and World War II. And honestly, like, you might imagine during World War II, suddenly the United States government was really interested in airplanes for some reason. Okay. So they created this organization which just studied airplanes. And they spent a lot of money. And they had wind tunnel testing, and they had, they didn't have CFD because computers weren't invented yet. But they had wind tunnel testing, they had a bunch of engineers, they had computers, even though the computer wasn't invented yet, because the computer was a human being, right? Have you ever seen the movie Hidden Figures? The later part of that movie takes place at NASA. The first half of that movie takes place at NACA, and NACA became NASA. So they did all these wind tunnel tests to get the behavior of all these different airfoils. Right. The last phrase I need to introduce you to is the span. And the span.
You're gonna have to change it.
Oh, of course I am. Thank you. The span is the length of the airfoil. Normal to the chord line. Or the camber line, it doesn't matter. I mean, literally, the span is if I extended this and I made it an actual wing. The span is the length of the wing. Okay? The airfoil is essentially the cross section of a wing. The span is the length of the wing. Okay? Now, what we're interested in is the forces on the airfoil. So, and most of my airfoils in this class from here on out, unless there's a reason to draw it, I tend to draw that cement. So I have an airfoil, and there's some wind, relative wind, that the airfoil is seeing. And because the airfoil is an airfoil, and because the airfoil is designed to do this, otherwise not a very good airfoil, there is going to be some force, some net force acting on the airfoil. Okay? Which for now I'll call F. Now, we as human beings have decided that we are going to decompose that force into two forces. We're going to take the component of that force that is in the same direction as the relative wind velocity. We're going to call that force drag. And then we're going to decompose the other component. And we're engineering students, so we all know all about vectors. This is just vector decomposition. And we're going to call, by definition, the component of the force that is perpendicular to the drag, we're going to call it lift. Regardless of whether or not it's up or not. Okay? It's always called lift, even if I'm not in an airplane. If I'm a wind turbine, this is going to be, the lift is actually not even necessary. The lift could be in the direction that the airfoil is rotating, the rotor is rotating, but not necessarily. The only definition of lift is the component of force that is perpendicular to drag, period. Okay? Now there's something else. There's another thing that we need to consider besides the lift and the drag and the force. At a point, which is 1/4 the chord line, and this is more or less by definition. At a point, which we always kind of take it as C/4, the chord line, the chord length divided by 4. We are interested in what is called the pitching moment, which has a tendency to want to pitch, to turn the airfoil. Okay, so this moment, and of course the moment would be, actually I'm not seeing right-hand rule. I'm not really sure if it could be coming out of the page or into the page, but this is the pitching moment. And this point that we say that the pitching moment is acting about, it's got a really clever name. It's called the quarter chord. That is that distance, right? And that's not necessarily true. That's not necessarily, where the center of rotation of the airfoil, but that's pretty close for most airfoils. So we typically just measure it, whatever the moment is, from that point, the quarter chord. Okay, so the big things, I think I've defined them in spoken words, so I'm not going to write down the definitions. The definitions are in the notes that I'll post after class on Friday. We have drag, we have lift, and we have the pitching moment. And of course, we're interested in knowing what the lift force is, what the drag force is, and the pitching moment is. Okay? Then we need to know that. And if not today, by the end of class on Friday, you'll know how to find out what these forces are for a given airfoil. Okay. Before we get to that, I need to make sure that you guys didn't sleep all through fluids. And just to remind you, because this is going to become important, of the Reynolds number. Okay, so just in case you slept through an entire semester, the Reynolds number, RE, is defined as the wind speed. And right now I'm going to say the wind speed like the predominant wind speed. It's usually the way we think about it. And in this case, it's the important length scale we're interested in is the chord line. Okay, so it's the chord, the wind speed times the chord divided by the kinematic viscosity, if you want to think of it like that, or you can think of it as rho wind speed chord line over the dynamic viscosity, if you're the kind of person who likes to think in the terms of dynamic viscosity. Okay, so again, here U infinity is the undisturbed wind speed. C is the chord, and rho is air density. And mu or mu are both air viscosity. Okay. The reason this is important is for what comes next. So, somebody really clever, might have been Reynolds, actually I think it was Reynolds, discovered that there's this relationship between these forces and the dynamic viscosity, or the dynamic pressure in the wing. And what they found was that for a given Reynolds number and angle of attack, that the lift force divided by, I'm going to say dynamic, dP for dynamic pressure, times the area of the air coil is a constant. But I'm going to call it CL, for little L's for lift. And likewise, the drag over the dynamic pressure times the area is also a constant. We call CD. It's called the drag coefficient. So this is, by definition, called the lift coefficient. This is called the drag coefficient.
What's DP?
What's that?
What's DP?
dP is dynamic pressure.
Okay.
But I'm about to replace it with a mathematical formula.
Okay.
And dynamic pressure is 1/2 rho by wind velocity squared. And you kind of see this written two different ways. So I have seen this, and the textbook makes a point of this, that you see this as CL equals my lift force divided by 1/2 rho U infinity squared times A. And the book notes that this is always written as C capital L. I don't know if this is actually true. You also see, the book says, when you see it as capital L, this is the definition. If you see it as lowercase l, this is the lift force per unit span. So this is your lift force divided by your span, divided by 1/2 rho U infinity squared. And then since this is by span, it's not your entire area of your wing. it's your chord. Okay, but these would have the same value. I should also say, this area, this A is not, I could see somebody thinking, oh, it's the area that the airfoil is facing the wind. It's not. It is this area. If this is the chord and this is the span, A equals the chord times the span. Okay, it is the cross-sectional, it is the area that your wing takes up. Okay, so you have this for lift. You also have these same definitions for drag. So if it's capital D, it's the drag force. Over 1/2 rho U infinity squared A, and if it's a lowercase d, it is the drag divided by the span. So it's basically the drag force per unit span of 1/2 rho U infinity squared, and then be the chord line. There's also the moment. So Cm, there is also, and this is also a constant, is the pitching moment divided by 1/2 rho U infinity squared, and this will be area times C. You need an extra dimension because now we're talking moment, right? So it's force times meters to get a moment. It's really hard to say moment without going, this magic moment. All right, now, all of these, no matter how you define them, these are all functions of angle of attack and Reynolds number. But I'm going to go a little bit further. I'm going to say it's a function of angle of attack, Reynolds number, but mostly angle of attack. So I'm just going to put like, look, strongly. And I'm going to go weakly. Okay. And I think I can actually show you some examples of what I mean by that. So what I'm going to show you, I meant to show you this later, but I think this is a good point to show it to you. So I'm going to go back. Yeah, I love this. I can go back and forth, and it doesn't shut the. Set it. That was stupid.
Better not all wood.
It's laminated.
Okay.
Okay. So this website is called Airfoil Database, and I can type in an airfoil name. I can also type in and you can go here. It's airfoiltools.com, and then that'll take you to this website, and I just click airfoil search. And I can type in, I want my maximum thickness to be this, and I want my minimum thickness to be that, and it'll find all the airfoils that match that criteria. I can also type in a particular airfoil that if it's a particular airfoil I want to know the name of. Oh, if any of you guys happen to be taking 306 right now, I think on any campus, and you're doing, nope, sorry, that's a different class. That's 406, you do the airfoil. Never mind. But next semester, you're taking ME 406, you end up doing the airfoil lab. The airfoil is a particular NACA. It's not a 0012. I don't remember what it is. I can click on here, and oh, here it is. Okay, so here's a NACA 0012. I can click on that, and it shows me this is the basic shape of a NACA 0012. And I can actually have it generate data points that you can then like import into something like SolidWorks, and you can create your airfoil out of that, and you can 3D print an airfoil on the data that's here. What I want to show you are these plots down here. This is the coefficient of lift versus alpha. Okay, and there's also a coefficient of drag versus alpha. Okay, so let's take a look at this one. And what you can see on this is that for a small angle of attack, and so small angle of attack of 0, which means that my airfoil is just like that. Right? Guys can see me in the video. Okay? Then this is a symmetric airfoil. So you can imagine for a symmetric airfoil, flat, no lift. Okay? And you can see that in fact the lift coefficient is 0. And then you can see that the lift coefficient increases, and it looks almost linearly as angle of attack increases. And what all these different lines are different Reynolds numbers. And as you can see, they all pretty much line up. Okay? There's a little bit of difference. Also, something that I think we'll probably end up getting to on Friday's lecture is you'll notice that it's all pretty much linear up to a certain point. And that point is referred to as stall. And the stall point seems to be more strongly dependent on Reynolds number. And by the way, if you go to this website, you can actually put in ranges of Reynolds numbers and set what you want the Reynolds numbers that it shows you to be. Okay? But the point I'm trying to make here is that yeah, there's a very strong dependence on angle of attack. Reynolds number it's important, but it's not as important. Okay? And that brings us to the importance, how cool it is that airfoils behave this way. Because if you're designing an airplane, if I'm designing an airplane, I know how much the airplane weighs. I hope. Okay? And if I know how much the airplane weighs, and I know how big the wings are, and I know which airfoil I selected, so I know, okay, when I'm taking off what the angle of attack is, I can figure out from this, how fast does the airplane need to go to get enough lift to take off? Which, you know, if you're like on a design build fly team, might be something you might just be interested in. Okay. And the fact that this is constant is incredibly powerful, okay? And incredibly convenient. And I'm pretty sure this is why Reynolds got a number named after. Okay? Is for this exact understanding. Although I could be wrong, I could have been something else. Okay, and I wrote lift as an example. The same thing goes for the coefficient of drag, and the same thing goes for the moment.
I have a question.
Yeah.
Is there a way to find the coefficient of drag without already knowing the drag force?
Yes.
Are we going to go over that?
You find what airfoil you want, and you look up the coefficient of drag. It's all done by experiment.
What if it was a custom airfoil completely?
Test it.
Okay, so we're about to, but we're not gonna have time today. So on Friday, we'll talk a little bit about the theory. But in reality, there is theory, but most of this stuff is known to be due to like, there's theory and there's computational fluid dynamics, but this all ends up getting tested in the wind tunnel. Okay, and we'll learn that the theory is really complicated. Okay, and things like this is the theory, but the theory, you know, so I'll try to summarize some stuff in about 5 minutes. If we assume that there's no boundary layer on the airfoil, we get what's called inviscid flow theory, and we can come up with a approximation of what the lift and the drag forces are at given wind speeds. But that is assuming that there is no boundary layer around the wing. Oh, but it turns out there is a boundary layer around the wing. Okay? And how big that boundary layer is depends actually not just on the shape of the wing, but also depends on like how the roughness of the surface of the wing. And so little imperfections on the wing can change that. So so we can get a good approximation. We can get a ballpark for a particular shape this is what the lift coefficient, this is what the drag coefficient is gonna be, but you really wanna do, tests on experiments on that before you state that for sure. Luckily, there is an almost infinite number of airfoils that somebody has done an experiment on. And somebody has collected this data on. And we're gonna actually talk about how in the course of the development of wind turbines, they've actually designed new airfoil shapes for things like, okay, this isn't necessarily the best shaped airfoil, but this airfoil seems to be less affected by there being damage to the leading edge of the airfoil. And therefore, as the wind turbine lives for 20 years and is spinning around at high speeds for 20 years, hitting dust, having ice build up on its edge, that it does a better job of maintaining a lift coefficient over 20 years. And people have been, okay, so now we need to study we need to study this new airfoil shape. And they built our wind tunnels just for that. Actually, somebody was showing me a picture earlier today of the world's largest wind tunnel, which is really big and can fit an entire jetliner in it. And they use that also to test new airfoil shapes and new wind blades for wind turbines. That's actually a really good question. And we're not going to get that far into this theory. I will, next on Friday, I will talk to you a little bit about why airfoils work. Although I can warn you, what I will tell you is very controversial, and a lot of really smart people will tell me I'm wrong. To which I'll say, well, those people are right, but also I'm not wrong, because you guys are both saying, we're all saying the same thing in different ways. So, anyway, that's a little bit of a preview to on Friday. But Friday we'll talk about why airfoils cause lift. And many other things.
Also, Griffith's was really funny. I was using the go on the different for hours. So,
You don't see.
The
only person in the meeting.
On your way home.